Good afternoon, good morning, or wherever you are. Ladies and gentlemen, my name is Paul Hillman with Eddyfi Technologies, and in this quick coffee break today, I want to give you a whistle-stop introduction to the new AUT platform from Eddyfi, the WeldXprt. It's designed for the rapid inspection of pipeline girth welds with the latest technology advancements and software capabilities in ultrasonic testing. So this type of system is specifically for the inspection of circumferential pipeline welds at the point of pipeline installation, whether that pipe is being laid overland or off the back of a specialist pipe lay vessel to the bottom of the sea. Automated ultrasonic testing, or AUT, has been deployed for the inspection of girth welds during pipe installation for more than 30 years, replacing radiography methods over time. The welding process itself on these types of welds is typically well controlled and automated welding performed by motorized crawlers on guided weld bands. And like many industries, time is of the essence for installation of these large engineering endeavors, where even small delays in fabrication and verification of welds can have large knock-on effects in the overall project schedule and, of course, costings. That's why we've invested a lot of effort in ensuring the workflow of inspection is kept to a minimum possible time, whilst ensuring the highest possible repeatability and confidence in the results. The goal is to get the quality acceptance or repair information to the repair team as quickly as possible to move on to the next weld and carry on production. Of course, with these types of welds, high quality inspection is demanded. And since once the pipeline is installed, the weld may never be inspected in the same way again, being either buried under land or possibly hundreds of meters under the bottom of the sea. Because of that, regular calibration is normally required for inspection of these welds using specific calibration blocks, verifying the performance of all UT channels being used. And indeed, for offshore inspection on pipeline lay barges, it's typical that a calibrate in and a calibrate out sequence happens next to every weld inspection that takes place. The calibration for overline pipelines can vary because you have access to these welds for longer periods of time. Overall, the typical inspection time must be less than 5 minutes per weld, encompassing the necessary calibration scanning sequences and verification of those, the inspection itself, the analysis, and the reporting of the results. Needless to say, demands on these highly skilled NDT operators and analysts are high. So WeldXprt is an advanced AUT system developed with efficiency and inspection at its core, and it sets a high benchmark for the rapid inspection of pipeline girth welds. Engineered for both onshore and offshore installation projects, flexible options of deployment, and supporting multiple advanced techniques out of the box, including zonal discrimination, phaser AUT, TOFT, of course, conventional ultrasonics, and TFM coming from either full matrix capture or plane wave imaging, as well as PCI reconstruction as well. These can be carried out independently or simultaneously. The system comprises, let's say, 4 main components: the software, the instrument, the motorized scanner, and the probes, and it's applied as an integrated and turnkey system for field deployment. The software is built on the UltraVision core and is a dedicated platform streamlined for this one application, featuring specific tools and capabilities, a few of which I'll highlight here in this coffee break. The flexible deployment options include either the instrument onboard the scanner with the Emerald platform, or instruments remote from the scanner with the Emerald or Topaz 64, with the use of a UT umbilical and integrated splitter box on the scanner, making it much more lightweight and deployable. The scanner itself is from Gyra Industries, and it's fully integrated and controlled from the WeldXprt software, running on standard CRC or RMS profile weld bands, with the ability to adapt to narrow width where cutback at the ends of pipes is of concern. Zonal discrimination, for those who don't know, is a technique widely deployed for this inspection, and one I'll use in the demonstration today. For those not familiar, in zonal discrimination, we divide the weld into discrete zones, each represented by a specific reflector in the calibration block, and each with a specific UT approach to target it. It's created from the phased array probes. You can see an example of those types of focal laws in the ray tracing that you see on this slide here in the animation. Alongside the zonal laws, it's typical to run complementary TOF, maybe phased array and conventional channels as well. So inside the dedicated software, we have a number of software developments to provide end-to-end functionality for this inspection. And a few I'd like to highlight include the ability to design these complex calibration blocks inside the software rather than having to do it in a third-party software, with an easy-to-use wizard-driven tool to put the reflectors in the calibration block automatically or manually to suit the procedure. This has two benefits. You can output the PDF drawings of the cal blocks then directly for the machine shop to manufacture the cal block, and the software already knows all the relevant information about those reflectors, so their position, their orientation, their size, ready to design the UT approach and for the next steps in the process, such as doing automatic calibration checks, so running over the calibration block. And that's the next one I like to highlight. So the ability to do automatic calibration checks. With these, because the software knows the position of the reflectors, their orientation, sensitivity, we can automatically check the calibration block to check all of those channels, which are each targeting individual zones, are properly tuned and properly sensitive to the indications they're supposed to find. So it's looking for the correct position, sensitivity, and time of flight for each one of those channels. If they're all good, it gives us a green cal success button. If something is wrong, one or more of those reflectors is out, we get a red calibration failure. So it's a go, no go, and we have the ability to verify then which ones are out of tolerance and by how much. On the back of the inspection, we've also spent a lot of effort in integrating advanced software-assisted analysis, and this is a two-step process. The first one is using rule-based assisted analysis to determine all of the indications that are in an inspection which are relevant for reporting. So with this, we can set different rules per type of zone, for example, and it does a similar thing that an analyst might do. So it will look for any signals that cross a certain threshold, are of a particular length or above, and are a particular position in time of flight in the gate. Anything that meets those criteria from the individual rules can be boxed automatically, added to the indication table, measured, and given a classification code relevant to the rule that found it. The second step in that process is to apply a code case to all the indications in the indication table, whether they were manually added or found with the software assisted analysis. In this, we apply a code case and it will automatically interact and accumulate indications as per the rules of the code, and it will automatically give a recommended sentencing of those, and if rejected, under which part of the code it recommends that. Any of these decisions, of course, can be altered or overruled by the analyst, but it's a tool to help them be efficient in deploying that and consistent across multiple analysts. There's also multi-screen support. We're all used to using multiple screens. I have 3 on my desk normally. And here we're able to use the full real estate from multiple screens for live data to be able to be efficient in analysis and sometimes acquisition when you have the space to have a multiple screens. So you can have your main strip chart displays, possibly with a large TOF display and phased array display as well, with augmented displays from multiple channels. So I want to show a time trial, a speed trial of this that we carried out in our lab with myself and my colleague, Daniel Richard. We're doing an inspection here of a 38-inch pipe with a 28.6 millimeter thick weld. We're first running on the calibration check. We're running a calibration sequence. You may see those gray boxes in the strip chart, and they are looking for the reflectors in the calibration block. It knows that are there. All of them are in the right position with the right sensitivity and time of flight. So we get a green calibration success icon, and that calibration file is stored. We now move the scanner to the real weld to be inspected. And Daniel will start the inspection sequence once the scanner is in position. We're doing zonal discrimination on both sides of the weld in this case, and TOF at the same time. We're running about 100 millimeters a second. You can see the 2 screens at the bottom there, which show the main screen on the left and the secondary screen on the right, where we have a large TOF display there showing the lateral wave and the first backwall echo, so that we can quickly monitor the indications that appear there and compare them against the strip chart, which also displays the tuft in the center. When we run around that block, we've gathered the data from the full weld volume. I'm going to move the scanner to the cal block again, and Daniel's going to move straight to the analysis step. And we're going to use a rule-based assisted analysis here. So he clicks the button for that. It's going to find everything in the data that meets the rules that we've set, and they're different per type of zone. It's going to flag them, give them a classification code, and measure them and add them to the indication table. The second step happens very quickly. He clicks apply code, where we're going to apply API 1104. The indications in there are interacted and accumulated automatically, and a recommended sentencing is given. The report is printed straight away. We get the PDF report there to give to the repair team, and we move for the cal out sequence. So we're going to do 2 calibration checks with this one. So quite a heavy load, but we're going to run the cal sequence now. We're back in position on the cal block. You'll see the strip chart running with the gray boxes looking for the relevant positions of the reflectors it knows in the calibration block. If they're all in the right place with the right sensitivity and time of flight, we get the green calibration success, and we complete the sequence, ready to move to the next weld for inspection. That total cycle time for that calibrate in, inspection, analysis, report, and calibrate out of 2 minutes and 18 seconds. So our goal with this system is to provide inspection teams with a highly efficient and reliable platform, which is flexible for deployment and with the tools available to tackle a wide range of configurations. So thanks for your attention. It's a very quick one, being a coffee break, so I don't know how far you've got down your coffee, but if we've got a few questions, I'll happily take them now. First question, what about transverse flaw detection? Yes, in lots of cases for these pipeline welds, we need to be able to detect transverse flaws, those that are 90 degrees to the weld direction. In this case, we use dedicated channels, typically using conventional probes with beams skewed in a pitch catch configuration, looking at the ID and OD. So we have setups for that, which we add to the scanner. And of course, there's a capability there to handle that in the software and the instrumentation. So they can be added. How does the TFM perform? Yeah, I've shown zonal discrimination here quickly. It's a very quick display, but the TFM can also be run with multiple types of construction at the same time. So typically we can run up to 8 constructions simultaneously in live TFM, either coming from FMC or plane wave imaging. With plane wave imaging is what we typically recommend for this, because we can go quickly at high speed, FMC a bit slower. And we get volumetric data, like a bit like phased array views, but not up to 8 frames at the same time from both sides of the weld. So we find the indications in a slightly different display, and the analysis is a bit different to the zonal discrimination. But that's how it works. So it can either be independent on its own, or at the same time as, say, TOFT, or at the same time as zonal if needed as well. Okay. Thanks for your attention. If you have more questions, please reach out to your local Eddyfi contact, or you can contact me at phillman@eddyfi.com, and I'd be glad to show you a bit more about the system. Thank you.